All right, let's finish up this example by looking at what the subprocess does on the MPI solution to the count key problem. So this is in the else portion of that program. Remember that the master sent out the key value first and then sent out the portion of the array that we should receive. Okay, so we're going to go ahead and do the inverse of that. We're going to receive the key value first in these three lines. So we declare variable k that's local to this process only because it's declared inside the brackets for the else. And then we have our MPI status object. So we receive k. Remember, we have to put the and sign in front of it because the first parameter to receive is a pointer. So it gives me the pointer to k. We're getting one value. It's an integer from process 0 with the tag underscore k. MPI com world is the communicator, and the status. Again, we need a pointer to where that status object is. All right, so that's just like the it was on the master process when it received the count back. Now, let's allocate memory. And our goal here, or our philosophy will be to just allocate the maximum amount of memory that we possibly could receive, and some of it won't be used on the last processor in the communicator. All right, so we do a calculation that's the same as the fragment size in the previous video. That will be the largest amount of values that I could possibly receive. Allocate that an array of that size. Okay? And again, if this is process 7 in a communicator of size 8, we won't use all of those, but that's all right. We waste a little memory. Now we're going to go ahead and receive our array segment from the master. And again, since the last processor in the communicator will likely be receiving an odd-sized chunk, we're going to need to have a way of figuring out how many values we actually got, which is we're going to hold in the lowercase n variable. So now, MPI receive. Excuse me. This time, since we need a pointer, we just pass in the array variable itself, no and sign in front of it. This is the maximum number of things we could receive. So we won't always receive that many necessarily, but that's the limit on the values we can receive. They're ints coming from the root. Tag array is the tag, so we know which message is which. MPI com world is our communicator, and our pointer to our status. Now we're going to actually use that this time. We're going to call a different function, MPI get count, pass in the pointer to the status object, and ask it to get the count as an int and put it in the variable n. So that will tell me how many things were actually received. Okay? And again, I hope you understand why that could be different in processors 1, 2, 3, 4, 5, and 6. In a communicator of size 8, they'll all be receiving the maximum value, but processor 7 won't, probably. And so the MPI get count gives us a way to figure out how many things we actually got. Right? So now we've got everything we need. So this part of the code goes through and does the search. We just initialize a local count variable, look at everything in the fragment that I received, check to see if it's equal to the key, add 1 to the count. And note that our array fragments that we're receiving are like normal arrays starting at 0, okay? So they're not indexed according to what they were in the master process. They're completely different copies of that data, okay? After I have count, then we'll send it back to the root process. So MPI send, again, the address of the thing I'm sending is &sign count. I'm sending one thing, it's an integer to the root process with the tag count tag, and this is my communicator, MPI com world. After that, delete the subprocess's memory, and that's all the subprocess has to do. Okay, so when those are both complete, when the master process is all done, it goes to the MPI finalize, and that will shut down the whole communicator. So now let's watch this work. We'll watch it local, and then we'll watch it on Onyx. Okay, so if I'm running on my local system with a Unix subsystem, MPI run -n8 will send up a communicator of size 8. And mpik.mpi is the name of the executable, and then I have to give it the value that I'm searching for. Okay, and you might get this firewall piece. That's okay, don't worry about it, just allow access and you're good. But it found that key value 1002 times, and that's what it expected, so yay, it worked. Okay? Now we're going to go ahead and investigate that on Onyx. I'm already on the VPN, so I can SSH into... Oh, I'm not already on a VPN. My bad. Let me connect. And as soon as this is done, all right, I'm connected. Now I should be able to do that. There we go. Provide my domain password. I'm logged in. And I've already made these pieces, or copied the files over. So do my compile. And I have a slurm job file, so let's look at that really quick. It's really the same as the other one. The only thing I've done differently is I've changed the name of the output file and, of course, changed the way I call the executable, mpi-ck.mpi, and the number that I'm looking for. Okay? So if I execute that slurm job file, by the sbatch command, it tells me that it submitted that job, and then when the output file is in the directory, we can see that it's here now. It should be done, so I can look at that. Whole bunch of stuff that we don't need to worry about up at the top, but down at the bottom, we see that it found the number 5,944 times, and that was the expected value. So it actually worked. I'm going to remove all of that before I exit out so I don't dirty up my Git repository. One thing to point out, I believe on the last video I was talking about how the emailing doesn't work. I think it is working now. It's just that the responses are automatically going to your spam folder. So fingers crossed, it actually works, but they're just going to the spam folder. All right, so that's an example of the count key using OpenMPI.